Yep, so I coordinate the module Measuring and Predicting Part 2. It's also in the first semester, but it's the second part of the semester and follows on from Steve's course. This course unit focuses on using and interpreting the output from numerical models that you use in the practicals. And I really believe that using by learning by using the models, it's really powerful. It's a powerful technique for you to learn how these processes act in say, the atmosphere or other systems. And so we cover relevant theory in lectures, but to see how the different mechanisms affect properties such as the climate, the weather, rainfall, and droughts is a really powerful learning technique. The models that are used in this module there's a cloud and aerosol parcel model. That's one of the models. There's also a Gaussian plume dispersion model. We're looking at how pollution is dispersed in the atmosphere. There's a single column model of the atmosphere where we can look at how pollution particles affect surface precipitation, so rainfall. And there's also a shallow water fluid dynamical model where we can look at weather forecasting and also tsunamis. And so we do some preparation to learn about techniques, the modeling techniques in general, and we learn about common pitfalls or issues with modeling. So, for example, what they can be used for and what they shouldn't be used for. And here you can see the web page for the model. This is actually an older version of the web page, but the key point is that it's a simple layout with all of the available materials for each week. And there's interactive activities that check that you understand the main points. I think I have another page, if you can move on. So there are extra pages each week that cover the practicals in more detail. And this particular one is of the single column model simulation. And the top left plot here shows clouds forming as the atmosphere interacts with a hill. The hill is the red data that you can see on this plot. And the top plot shows what we call the cloud droplet number concentration. It starts off at about 100 per centimeter cube, and it drops off very quickly. Why? Well, if you move down to the bottom left, you can see why, and that's because raindrops form. So this is the raindrop concentration from the model, and we can see when the air is lifted over the hill, we start to get the rainfall, and it falls on the upward side of the hill. And downwind of the hill, we tend to see there are no clouds. So this can produce situations where you have a vastly different climate, both upwind and downwind of a hill. So top right is the total mass of the cloud, the mass of the cloud water. And as you can see, as the air is lifted over the hill, it becomes lifted over the hill, more liquid water is condensed. And that's because the air gets colder as we move higher up through the atmosphere. And more liquid water can condense onto the particles, they become larger and eventually fall as rain. So we learn about the different factors that affect things like precipitation, things like pollution aerosol particles or different types of aerosol particle in this particular practical. And we also learn about different atmospheric processes. And each week you do a similar practical to this. And the idea is that you learn about the models and you use them and you learn about how to interpret the output. And that's the end of my section. Thank you.